reminder of where we left off. We finished with the ratio test, which was a very powerful test. It involved us taking a limit, and that's the first test that we're going to look at it again today. And then what's going to lead us to our second test, which is the limit comparison test. So just as a reminder with the ratio test, we took a limit, and we're looking to see what the answer was. The answer can either be less than 1, greater than 1, or equal to 1. Equal to 1 happens every now and then, but mostly we either get the less than 1 or greater than 1. If the result is less than 1, our series will converge. If the result is greater than 1, the series will diverge. The example that we did was number 29. We were dealing with exponential functions or really high exponents. And if you recall from this, here's the limit, here's the n plus 1 term, and we multiply by the reciprocal of the nth term. And that allows us to think of 5 to the n plus 1 as 5 to the n times 5. That's a time for that. And then we can eliminate the 5 to the n's. We can do the same thing with the 3 to the n, 3 to the n plus 1. So we're left with the 3 in the numerator, 5 in the denominator. And those get distributed with the n to the 100th. We look at our leading coefficients, and we end up with a limit of 3/5. Since 3/5 was less than 1, up here, that meant that our series converged. So this ratio test works really well with when we're dealing with exponentials, or we're dealing with factorials, or really large exponents. This will all work out well. And it involves us taking the limit. There's another test that involves the limit, and that's on the top of the next page. It's the limit comparison. And the idea behind the limit comparison test, when we take the limit this time, is we're looking to see not whether we get a number less than or greater than or equal to 1, but rather if we get a number which is positive. So what exactly are we taking the limit of? Once again, it's a ratio, but this time it's a ratio of two series. A series that we don't know whether it converges or diverges, which we'll call the A sub n. And then a series that we do know converges, which we'll call B sub n. And here's the deal. If we take the limit and we get a number, any number that's positive, that means that both series will either converge or diverge. Alright, so what's the general idea? We're going to take a series that we don't know, for example, this one down here, and we're going to compare it with a series that we do know. Alright, so what series should we look for that we do know? We should really focus on P series and geometric series, because we know real quickly whether or not these series will converge or diverge. Now with the P series, that's 1 over n to the pth power. If P is greater than 1, then our series will converge. So for example, 1 over n squared or 1 over n to the 4th, those series will converge. If P is less than 1 or equal to 1, then the series will diverge. Right, so for example, 1 over n, remember that one was called a harmonic. It diverged. Those are real quick ones to use. Let's use it right here. Right, we have this series, n goes from 1 to infinity, of the quantity n cubed plus 2 over 3 plus n to the 4th. So let's find the limit as n approaches infinity. This is our A sub n series here. It's our unknown one. So we've got n cubed plus 2 over, let's write this n to the 4th plus 3. I'm going to compare it to the series of 1 over n. You may know why I picked that. You may not know why, but you will very soon. Now, by the end of this video, then by the end of the next one. So what happens with this limit? Right, we have the limit as n approaches infinity. Since we're doing fraction divided by fraction, let's do the same thing we did with the ratio test. And multiply by the reciprocal of the denominator. Now, when we do it this time, we're not going to be able to cross anything out. But we do have multiplication here, so we know that we can do numerator times numerator and denominator times denominator. In essence, we can distribute that n. So we end up having n to the 4th plus 2n in the numerator, and we have n to the 4th plus 3 untouched in the denominator, because we're just doing n to the 4th plus 3 times 1. Now we have a limit that we've been discussing for almost 2 years now. It's a really easy one to find. We see the highest exponent is both the numerator and the denominator, so the leading coefficients, which are both 1s. 1 is equal to 1. And that's our C. C is bigger than 0, so that means that both series converge or diverge. What is the series that we used? It was 1 over n. You know that that series will diverge. It's the harmonic. So since we used a series that diverged with our series, when we got numbers, we took the limit of their ratio. That means that this series will also diverge. And it's going to diverge by a limit comparison test. We'll do another one, problem 31 in just a second.